We now need to do the same for the internal QC, IQC sample. So again, just the same, 3 glass test tubes, 1 for each dilution that we're about to prepare. So we've now got the IQC sample. So remember, this mixture was 200 microlitres pooled normal plasma, 200 microlitres IQC sample. The IQC sample was diluted 1 in 20 before we made the mix. It's to take account of the expected level in this sample. That's based on our previous results on this IQC material. So we know that the IQC material contains antibody, contains anti-factor VIII, so we expect that there will have been loss of factor VIII, additional loss from this mixture relative to the control. That's what we'll now check. So this material, just as the control mixture was, 1 in 5, 1 in 10, 1 in 20, same dilution buffer, the buffer that's used for factor VIII assays, and mix. So we make a set of dilutions and test. Obtain the clotting times. Move to the next tube. Make a set of dilutions and test. We should not make all the dilutions. Test the first, test the second, test the third. It introduces additional variability. So we're trying to treat each of these materials the same as the control mix. 3 glass tubes, factor VIII deficient plasma, 100 microlitres in each tube. Trying to reproduce here the same conditions as we used for the control mix. Warm to 37. First tube, 1 in 5. Second tube, 1 in 10. Third tube, 1 in 20. So we'll be treating this now and all of these other mixtures in the same way. In turn, make the dilutions 5, 10, 20. Add to factor VIII deficient plasma. Warm to temperature. Activate with APTT reagent, 3 minutes for this reagent. Clot with calcium, record the clotting times. We need to convert the clotting times into percentage residual factor VIII. And we're going to make a comparison between the IQC and the test sample mixtures and the control mixture. We're interested in the loss of factor VIII from the QC and test mixtures relative to the control mix. So we can use the control mixture as our calibration material for the purposes of this calculation. So we're not now working in international units per deciliter, we're looking at the relative concentration. So the 3 dilutions of the control mix, 1 in 5, 1 in 10, 1 in 20. We ran a control mix, effectively a calibration material, both at the beginning and at the end of the assay, with all the IQC and patient mixtures assayed in between those 2 standard control mixtures. And that's so that we know whether the assay conditions have stayed constant over the period of assay. We want to first ask the question, rather like we did for factor VIII assays, are the clotting times in the standard control mix at the end of the assay, are the clotting times similar to those which we obtained at the beginning? So if we start with the 1 in 5 dilution, we obtained a clotting time of 63 seconds at the beginning of the assay, and at the end, 62. Very similar. These times should be within 5%. These are close enough. So we need to take that clotting time to the graph paper. The graph can be plotted using log paper. That's what we're now using. We notice that this gives good lines usually, for the reagents that we've been using for this demonstration. It could just as easily, for many reagent sets, it could be plotted using log linear scale. This also frequently gives a good line, good calibration line. So we're using log just now. So we have the horizontal axis with a scale where we plot the concentration or dilution. So if we take the first one as 100%, then the other gradations, 90%, 80, 70, 60, 50, 40, 30, 20, 10%, 9, 8, 7, 6, 1%. Coming back to our assay dilutions. On this occasion, in this factor VIII inhibitor assay, the first dilution we used was 1 in 5, and it's conventional to take that first dilution and plot that in the 100% position, whether it's 1 in 5, another assay, different reagents might be 1 in 10 for the first. Either way, we consider the first dilution 100%. In this case, 1 in 5, 100%. 62 seconds, 63 seconds. We plot the clotting time on the vertical axis. If the first one is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, this is log scale, 200, 300 and so on. So this is the clotting time in seconds. 62, 63, 62 and a half, the average clotting time. Here on the 100% line, 62 and a half. Now we consider the second dilution, 1 in 10 dilution. First dilution 1 in 5, next dilution 1 in 10. So what's the relative concentration? 5 over 10 times 100, 50%. So we plot the 1 in 10 dilution here at the 50% line. Clotting times for the standard control mix, 69.5, 69. Same time, more or less, average 69, 69.5. Just under 70 seconds. Third dilution, 1 in 20. First dilution 1 in 5, so what's the relative concentration? 5 over 20 times 100, 25%. 1 in 20 dilution. Clotting times, 76.2, 77.5. Very similar. Average clotting time, 77. Is this a straight line relationship, for which we need the ruler? Do we have a straight line between joining the 3 points? Yes, it's a straight line. It's not perfect, but the points are very close to this, so we've got a line of best fit, straight line relationship. So we can proceed. QC material. Before we can move to any patient samples or patient results, we need to ask the question, have we obtained the correct answer? Has the assay worked? And this comes from the IQC material. 1 in 5, 1 in 10, 1 in 20. Clotting times, 71 seconds for the 1 in 5 dilution, plotted on the 100% line. Second dilution, 1 in 10, plotted on the 50% line, therefore, 78 seconds. Here. Third dilution, 1 in 20, 25% line, 89 seconds. Here. Do we have a straight line relationship, and is it parallel to the standard? We need to meet both criteria for the assay to be valid. So we're looking for a line of best fit. Is it parallel to the standard? Straight line relationship, yes. Every point exactly on the line, no. Some small differences, half a second, that's typical. Straight line relationship, yes. Parallel to the standard, yes. We've got a valid assay. We need to ask the question, in this IQC material, what's the concentration of factor VIII here relative to the control mix? And we do that by looking for the point where the line of best fit, where does that cut the 100% line? And that's here, on or close to that first point. In this case, just below, around 71 seconds. And then we ask the question, what's the concentration of standard which would clot in 71 seconds. And the simplest way to do this is to take a cross here and then to drop a perpendicular here. 46%. It means the residual factor 8 is 46%. We're not working in international units per deciliter. We don't need to. We're not now making any adjustment for the level of factor 8 in the control mix. We don't need to. We simply want to know what have we lost in the QC and test mixtures relative to the control. So we'll leave this in percentage. IQC, 46% of the standard. Now remember that the international definition of 1 Bethesda unit is that amount of inhibitor antibody which destroys 50% of the added factor 8 in 2 hours at 37. Remember, we incubated 2 hours at 37. Destroys 50%, residual factor 8, 50%. So if that figure were 50%, it would be a concentration of 1 Bethesda unit. We need to set these assays up in such a way that the residual factor 8 at the end of the assay is somewhere close to 50%. So on this occasion, 46%, very close. So we will later be able to use that to successfully quantify inhibitor in the QC sample. And we'll come to that in a moment. First, we need to calculate the percentage residual factor 8 for each of the test mixtures. We made 4 different mixtures of patient test with pooled normal plasma, 4 different mixtures. The first one contained patient plasma which had not been diluted, undiluted plasma, and these were the clotting times. For the 1 in 5, 87.5, so here. For the 1 in 10, 94.9, here. For the 1 in 20, 104 seconds, here. So for that first mixture of patient with pooled normal plasma, is it a straight line relationship? And is that parallel to standard? So we've more or less, it's not a perfect line, but we've got more or less a straight line relationship, parallel to the standard. Not every point is on the line. Perhaps 1 or 2 seconds here, also 1 or 2 seconds here. That's typical of the assay. Straight line relationship, parallel to standard. Where does it cut the 100% line? In this case, 84 seconds. It means the residual factor 8 in this mixture is around 13%, 13% of the control mix. We know the assay has limitations. One of the limitations is that the relationship between residual factor 8 and inhibitor theta is not linear across a full range of inhibitor concentrations. In fact, we know that we can obtain good information, good data, if the residual factor 8 lies somewhere between 25% residual and around 65, 70, 75% residual. Below 25, and publications tell us, we risk significantly underestimating the real concentration. And we really need to have residual factor 8s much closer to 50% in order to obtain a quantitative answer. So on this occasion, for the patient sample undiluted, 13%, significantly below that figure of 25. We know we've lost a lot of factor 8. We already know that inhibitor is present. Clearly there's quite a strong inhibitor. Majority of the added factor 8's been destroyed. But we can't use that 13% to reach a conclusion about the concentration. It's in that area below 25.